This lecture is over the thermal analysis of buildings, specifically over fenestrations, their transmission and transmittance of energy. Fenestrations, when we have heat loss, they lose energy through transmission through the glass itself and the window as a whole to the exterior of the building. And of course, it's run by the heat loss of the delta T of the different temperatures from inside to outside. Another way in which we lose energy through windows or fenestrations is through air leakage, infiltrates around the cracks of the window itself. From a heat gain point of view, there are three ways in which we gain heat. One is, once again, the U factor, the delta T being higher outside than it is inside, and therefore transmission of energy through the glass or the window itself. And of course, then air infiltration, where hot and sometimes moist air is infiltrated into the building from cracks and openings around the window. And then the third, which is unique to the glass, is because it's relatively transparent, is the direct solar gain that comes through the window. And of course, when light passes through the window and strikes another surface, it turns into heat, so it can heat up the building. So we talked about heat transmission through the window itself. That's called transmission. Light energy in the form of light passing through the glass, that's called transmitted energy. It's signified normally by what is called the solar heat gain coefficient. There also, and I'll talk a little bit more about it, used to be a shading coefficient, but that's often not available anymore. The more effective solar heat gain coefficient is used instead of solar shading coefficient. So when light strikes, of course, the window, it also is absorbed into the glass itself, and then it can be re-radiated or emitted from the glass and the frame into the building or out from the building. This is called emittance. And then, of course, the air infiltration around the frame. So let's look at the transmission through the frame itself. So if heat is transferred through it, either from inside to outside or outside to inside, it follows, once again, this formula of the area times what is now called a U factor and times the delta T. And of course, the U factor is a U value that is obtained through the operations of a testing in a factory, in a laboratory, and is tested within the laboratory as an assembly of the window. The U factor is between usually 0.2 up to 1.2. 0.2 is a window that is well insulated, because the U factor, of course, is the lower the decimal number, the more effective the insulating of the window. In the IP, or what we call the imperial units, the units that we use, the amount of energy that passes through is calculated as the BTUs per hour, square foot of window per degree Fahrenheit. Okay, BTUs hours per square foot Fahrenheit. And the U factor is included in the energy performance rating on the label of all windows in the United States. You have to have your windows certified for their U factor. Okay. So how do we look up this U factor to put it into this formula? Well, one way is, of course, to get the U factor from the actual manufacturer, and in this case, that is going to be a tested or a certified number. So that would be a good way in which to get it. The other is, of course, to go to the ASHRAE Handbook of Fundamentals and look at the U factors, and they have generic U factors for generic windows. Okay, but they'll be within 10% of the typical window. And you'll see, to read these, there's a whole series of charts, 2 or 3 pages of it. And the first thing is the glazing type. What type of glass are you using? And you need to know not only whether it's double glazing, but if it has an E value. And we'll talk about an E value. You've probably heard of low E glass. This is what it's referring to. Uh, and you'll see different E values, and you'll see it on different surfaces of the glazing. And so make sure that you pick the one that you want. Uh, and then the next thing we're going to choose, once we say, okay, we want to use double glazing with an E of 0.2 on surface 2 or 3, then the next thing is to choose what's the airspace. You'll see a 1/4 inch airspace or a 1/2 inch airspace, and then you'll see another 1/4 and a 1/2 inch with argon gas. Argon is a gas that they put inside double pane windows. It's an inert gas, so it doesn't transfer energy as easily, so it's a better insulator. And you'll see in many cases this will be more effective U factor, a lower U factor than just air itself, dry air. The next thing we're going to choose is then what type of frame we want, and you'll see 2 types, operable. So this is all the operable frames right here where this break is, and then fixed. And it's basically the same frame material: aluminum without a break, aluminum with a thermal break, reinforced vinyl, aluminum with a clad window, clad wood, or wood and vinyl, and then insulated fiberglass and vinyl. In our case, we're just going to use a typical aluminum with thermal break. And if we go down here, we'll see that the U factor for that is 0.48. Okay, so that is its resistance to transmission of energy is 48. In a sense, 48% of the energy will pass through. So the other is what we call the shading coefficient. In other words, how much light does this glass block and from transmitting through the window. And as we said before, windows have 3 conditions, or the glass has 3 conditions. One is the light can be reflected, the light can be absorbed and converted to heat inside the glass itself, and then of course it can pass through the glass. Whoops. In the case of a shading coefficient, all a shading coefficient does is identify how much light or light energy is going to pass through the glass itself. It's one simple value. It's often referred now as T, or transmittance, and that's how much. But that's not adequate. What we really need to understand is all the ways in which energy is passed through the glass, and that's not only how much is transmitted through the glass itself, but also how much energy is taken off from convection from the glass, as well as emitted from the glass back into the space itself. And so they developed what is called a solar heat gain coefficient, which is established inside of a laboratory. It's laboratory tested, and it takes all of these things into account: the absorbance of the window, the convection, long wave emittance into the space, as well as transmittance. And that value is expressed between 0 and 1. The lower the SGC, the better. Or that's not better, it depends on the conditions, but the lower, the less light is going to come through, the less energy is going to be transmitted. Okay, the SGC value is often transmission value is less normally than the just the shading coefficient, and if you have a shading coefficient, then you can just multiply that times 0.87 and get very close to what the solar heat gain coefficient would be. I've been talking about this thing called emittance or emissivity, Emittance is when energy radiates off of a surface into a space. It doesn't just apply to glass. It could be a wall. It could be any surface that emits, okay, emits radiation or heat from it. If a wall was had sunlight shining on it and was heated up, it would start emitting that heat from it. Okay, and that's called emittance. Uh, in the case of glazing, what we're interested in is the emissivity of the material. In other words, its capability to emit energy or radiation, and that's expressed by this kind of fancy E here, about, or just a simple E, as we saw in those tables, and that tells us the level at which this emits. Also, it which surface it's on, whether it's surface 2 or 3, will tell us which direction it emits. In other words, you can put coatings on this so that the long wave emittance doesn't happen towards the building or into the building, but actually outside of the building. Okay, and that's what emissivity, or E, is. So solar heat gain coefficient. So if we want to know, once again, we can go to the manufacturer, get their certification of what their solar heat gain coefficient is for their glass, for their windows or their doors, their glass doors, or we can go to these generic tables within ASHRAE, and there's multiple pages of these kind of describing different. This is just one section of one page, and you'll see here the first thing we do once again is determine, well, what's the nature of the glass itself. And in here, this case, you'll see low E double glazing with an E of 0.2, but here it says on surface 3. It doesn't say on surface 3 and 2, okay, because it makes a difference. The solar heat gain coefficient makes a difference whether it's on 2 or 3. And 3 means it's going to reflect or emit energy to the exterior of the building. If it's on a 2, it's going to emit energy into the building. Okay, and so if we look, then next thing we're going to do is determine the thickness of the glass itself. Is it 1/8 inch thick or is it 1/4 inch thick? And of course, the thicker glass is usually used in much larger windows. If you've got a 10 by 5 double pane window, then you're going to need thicker glass than that to withstand the winds and stuff. So we'll just stay with down here. We'll just go down and just show you this 1/8 bronze. Okay, so a bronze LE means that the glass has been coated with a bronze, and so it's going to be more highly reflective. Okay, it's not going to transmit as much as the energy as a clear glass would. And then we're going to go over here, and you'll see once again the center of glazing properties. Okay, and you'll see total window solar heat gain coefficient at normal incidence. Okay, and of course normal incidence means perpendicular to the glass itself. Okay, so it's assuming that the radiation is perpendicular to the glass. Over here you'll see different angles. So if you wanted to see what it's the effect of different angles to the glass, you could look here, but we're really not interested. All we need really is this right here. Okay, this column right here is about the transmittance, the visible transmittance of light. Okay, and we'll talk about that when we get into day lighting, but right now this is what we're interested in, is the solar heat gain coefficient at normal incidence. And you'll see aluminum frames, and then all other frames, and then operable and fixed, and operable and fixed. Okay. So let's assume once again aluminum, because the thermal break doesn't make any difference. Aluminum, it's operable or fixed. Let's assume that it's a fixed window. It's in a commercial building. It's hermetically sealed, and so we're going to come down here, and here's its solar heat gain coefficient if you're using this glass type right here. If we were using a double E glass clear, okay, notice fixed, this would be 0.64. So this is going to allow more energy in, right? It's from 0 to 1. 0 would allow no transmittance whatsoever, and and one would allow 100% transmittance. And so, of course, 0.64 transmits more energy into the building than a 0.52. Okay, so this is a blocks more, a little bit more of the light. Okay, the I spoke about this. The National Fenestration Rating Council is the most common certifier of windows, but they're not the only ones. There are other people, UIL. There are other people who certify them. And they certify all these things. The U factor right here, the solar heat gain coefficient, okay? And you'll see visible transmittance. And once again, this is usually just used for daylighting purposes. If you want to know how much, even though the solar heat gain coefficient is very low, the natural visible light that's being transmitted is pretty high. 50% of the visible light is being transmitted, whereas 0.32 of the whole range of energy is being transmitted there. And then of course it's air leakage. In other words, it's got a 0.2, which is a really good tight window. And then condensation resistance has to do with its resistance to condensing on the interior. And this is an issue mostly in cold climates, especially cold climates where there is a lot of moisture, or any where there's a lot of humidity or moisture. If it gets cool enough that the dew point is reached, you can have condensation on the interior of your glass. Here in Lubbock, Texas, or El Paso, that's not too much of a problem, because once again, we don't have a lot of moisture or humidity. So how do we calculate the energy that is lost and or gained through the fenestrations? Well, these two formulas, okay? Heat transmission, in other words, the actual energy that's transmitted through the glass and the frame itself, is times the area times the U factor times the delta T. Okay, so the delta T is the driving force in this. Okay, it's what drives the whole kind of how much energy is passed through. The U factor controls the flow, and of course the how much do we have? Do we have 200 square feet of window, or do we have 1 square foot of window? On the same side, you'll see the calculation is pretty similar. Okay, once again, heat gain. Here it's only heat gain because it's the sun's radiation that's striking, and the heat gain is the area times the solar heat gain coefficient. Okay, once again, we can get from the rating of the window or look it up, and that is like the U factor in a sense. It's the percentage of light or energy that's allowed into the building, and this is once again the percentage of energy that's going to be blocked or resisted from transmitting. And then the next thing is, of course, the solar heat gain factor. In other words, how much energy do we have coming from the sun striking that window? Okay? And to calculate that, what we're going to do is go to a series of charts. They're in ASHRAE. The simplest way to do this is if you have a computer program that has all this weather data. All this weather data is, of course, digital now. So if you have some kind of app or digital program where you can just look it up, then it will tell it to you. You can probably go online and find it if you wanted to. But in ASHRAE, Handbook of Fundamentals, there is a solar intensity and solar heat gain factors for 32 degrees latitude. You'll notice these tables are about 4 degrees apart, so it's all dependent on the latitude that you are, because that affects the angle of the altitude of the sun. How you read this chart is, you'll see right up here, this is, does the glass face north, north, northeast, northeast? Okay, this is of course 15-degree increments. Okay, east, east, southeast, southeast, south, southeast, so forth. So let's assume that we have south facing windows, and we want to know how much BTUs strike that window and would pass through it if it was clear or 100% transmitted. And then you're going to look up, they use the 21st of each month as a set date. And then you'll notice the time here. This is AM. So 7 a.m., 8, 9, 10, 11, 12. 12 noon right here. And then if we go over here on the other side, we'll see 12 noon, 1 p.m., 2 p.m., 3 p.m., 4 p.m., 5 p.m. Because as the sun arcs across the sky, it's symmetrical in the sense that it follows the same path at solar noon back to down until it sunsets. So let's assume we just want to know at the highest day time of the day, 12 noon on March the 21st. There's 176 BTUs per hour per square foot, okay, of glass. Okay, so that's how many BTUs of energy in the form of light strike that surface. So we can put that here in this formula. The heat gain is equal to the area, okay, times the solar heat gain factor, and we determined that was 0.32 earlier. So if we have 30 square feet of window times 0.32 solar heat gain factor, only 32%, okay, of the energy passes through the window, and we have 176 per square foot. Okay, so 30 times 176 would tell us how much total energy we have trying to get through the window, and then if we multiply that 0.32, then only 32% of that energy is actually going to pass through the window. Here, if we look at heat transfer, okay, we have the area, the U value, and the TI and TO. Okay, so the solar heat gain factor in this case is the driving force, how much energy we have trying to get into the window or through the window into the building. Here we're interested in the differential between the interior and exterior temperature, the interior temperature being here, TI, TO, right? And that becomes the driving force for transmission. This is transmittance. This is transmission. One's with an SS and one's with a TT. Okay, and so if it is 30, let's look at it. If it's 72 with 90-degree temperature outside, okay, then 30 square foot window, same as this one. In this case, the U factor is 0.35. So we're going to multiply 30 times the delta T here, and then take 35% of that, and that's going to be a minus 294. So we need to be extracting out, okay, from the building. It's going to have 294, and on top of that, because of the solar heat gain coming through the windows, we're going to have, oh, I didn't get a value here, but we're also going to have all this heat gain, and you'll if we were to multiply these numbers, we would see this is going to be hotter. This is going to provide more heat gain than the transmission through the window actually. The last thing I want to talk about is what is called a projection factor ratio. In the building codes, there is the new model energy building code. It limits the amount of window to wall ratio is what it's called. In other words, how much window we can have to wall. And it's usually in the neighborhood of 25 to 30%. In other words, you can only technically have, according to energy code, 25 to 30% of the wall in glass. And if you want a full glass window, then what you have to do is calculate and the savings that you get from having that window, using it as daylight or whatever. But if you don't show them that you can keep the same level of energy usage as you would have with just 25% window, then you can increase the amount of window in the building. Okay, so that's something to really think about, because a lot of us, we get into designing and all of a sudden we want all this glass and stuff like that. And unless we can show we're using it in a way that will not cause that building to use more energy, then we're not going to be able to include that in our design. One way of increasing the amount of window in on a building is to shade it, is to provide shading for it. And of course, the simplest way to shade a window is some kind of overhang. And so in the code, they have this little formula for a projection factor. And what it does is it projects the amount of shade, okay, that this projection here, or this overhang, would provide for the window. And it's just two measurements. One is from the sill of the window to the bottom side, okay, to the bottom side of the overhang, and then from the glass to the outside of the overhang. And so if we have that value, let's say it's 2 feet, and we have this value, which is 4 feet from here to here, then if we divide those, the 2 feet by the 4 feet, we get a projection factor of 0.5. Okay, that means that this overhang will shade this window about 50% of the time, or 0.5% of the time. And in the handbook, I'm sorry, not the handbook, in the energy model building codes, they will tell you how much you can increase the glass based on this factor. Now, of course, if this was 4 feet and this was 4 feet, this value would be 1, which means that it would be 100% shaded all the time. Okay, so 1 would be 100% shading, 0 would be no shading, and then anything in between is a percentage. Yeah. So, and we'll talk more about the shading in the next lectures to come. Okay, so of our external loads, what we call the loads that come from the climate. Okay, we've talked about the surface, or the assembly, the walls, roofs, all the opaque, okay, surfaces, and we calculate that using this formula of the BTUs per hour that it transmit is equal to the area times the U value. Notice I said U value, not U factor, because this is derived from adding all the R values of the materials together and taking the reciprocal, and times the delta T. Okay, once again, it's transmission. Through the glass or fenestration transmission, it's the same formula. You'll notice that area of the glass, the TI and TO, because we're looking at transmission, and the driving force in transmission is, of course, the delta T. And then we've got a U here, but it's the U factor. And of course, this is a tested U factor, or U value, that comes from a certified test inside a laboratory. Okay, so you'll notice it's the exact same. It's just where you get this U value is different. Here we're going to get it from the window manufacturer or ASHRAE handbook. Here we're going to get this through adding up all the R values of the different components of an assembly for a wall or a roof or a ceiling, and then take the reciprocal of the R values to get the U. And then there's the transmittance, in other words, the light that will come through the glass itself. And that's, of course, the area, how much the window will block that glass, that transmission or transmittance, is the solar heat gain coefficient. And then how much BTUs per hour per square foot do we have of energy striking the window. So this is the driving force here, whereas the difference in temperature is the driving force. Here it's how much energy is coming from the sun, radiation coming from the sun. Normally we associate that with light that will pass through the window. Okay, and these are what we call our external loads. The solar heat gain coefficient of the window determines the percentage of the heat gain uh, from sunlight striking a fenestration or from transmission of the energy through a fenestration. And so which one is it? Solar heat gain coefficient of a window determines the percentage of heat gain from sunlight or from the transmission of the energy through the fenestration. I'll let you answer that. The U factor of a fenestration determines the percentage of heat gain from sunlight striking a fenestration or from the transmission. So the solar heat gain coefficient controls which one of these, and the U factor controls which one of these. The driving variable for the amount of heat gain through the glass of the window is, okay, so what's the driving variable for the amount of heat gain? The key is heat gain through the glass. Okay, heat gain through the glass. So energy that's passing through the glass of a window, is the driving force the solar heat gain factor, or is it the delta T? And you should be able to answer those questions. Thank you.